All right, so this really is the conclusion of what I want to present, that I believe the data suggests that radiogenic heat, so the internal heat produced from the decay of radioactive elements, really drives or plays a really important role in the thermal evolution of the Yilgarn. Okay, so why is this important? Well, it indicates that the redistribution of mass and heat may have been largely internally driven. Now, that's not to say it doesn't require, or it doesn't allow for the input of additional heat sources, but it does not necessarily require it. And this also implies that the Yilgarn crust may have sustained elevated temperatures for hundreds of millions of years. So that really affects the way that the crust behaves or is characterized. So keep that in mind. Okay, so there's a number of data sets that have been used to kind of test this hypothesis. We've heard about a lot of them. The one I want to just focus on for a few minutes is the metamorphic pressure temperature age data, because that's really where this project kind of was born, and it has evolved to incorporate these other data sets. Okay. Now, I don't want to do death by metamorphism, but I'm going to step through some of this stuff very quickly. So the methodology that we incorporate is a phase equilibrium modeling approach, and this is basically the construction of phase diagrams constructed for a specific bulk rock composition. So every sample that we look at is kind of customized for that sample. So this is very laborious work. So the idea is to take the interpreted peak metamorphic assemblage. We use TEMA data or mineralogical maps to help us with this. We can try to come up with a peak metamorphic assemblage. We match that with the phase diagram on the left in pressure temperature space. And if we can find information on how minerals have grown or been consumed, that might give us some further information. Now, the messy reality of working with this kind of metamorphic data is that we're often looking at metamorphic assemblage fields, fields in PT space. We do try to refine this when we can with either mineral modes or chemistry, but an unfortunate reality of metamorphic samples is you're looking at large uncertainties. We report our metamorphic data, so the ones that you see on the map here, these are median values. Okay, so these are the median temperatures and the median pressures. And we also report the min and the max, so that we kind of call that uncertainty, but it's really just the range of permissible values. Okay, and that kind of degree of uncertainty or the size of this peak metamorphic field is reflected in the symbology that we use. So a really large symbol on the map actually corresponds to a well-constrained field. And the idea is to kind of draw your eye to the data that we consider the most reliable or the most robust. And then as those constraints get more, as the fields get bigger and we lose a bit of certainty, those data points tend to get a bit smaller. Okay, so just want to kind of point that out to you. The real value of metamorphic data is not just because they're cool and fun rocks to look at, but they really capture a record of the thermal history that you see in the crust. Okay, so this diagram on the right are kind of various thermal regimes. The dashed lines represent thermal gradients or thermobarometric ratios. That's the pressure over the temperature. And that's a way to normalize data if you're looking at different crustal levels. You see a rock here, it's got a temperature of X. 20 kilometers away, it's got a temperature of X. They might actually be telling you the same thermal history. Okay, so it's these gradients that really tell us a lot about what metamorphic data represents. And just the colors that we highlight are metamorphic fields. So the yellow field on the left actually corresponds with the range in PT space and a range of thermal gradients on the right. Okay, so in terms of the metamorphic history data set, this is available. So far, we have 41 data points in the Yilgarn. This represents one of the largest robust metamorphic data sets in the world for a single terrain, as far as I'm aware. We are constantly refining this, okay? And the technique that we use is comparable to what Naomi does at UWA, what anything out of Curtin would be coming from, so we can incorporate these data as well, although that's not presented here. We've got 68 points so far across the state, so this is becoming quite a large, robust data set. We report the pressure, the temperature, and the thermal gradient, which again is this thermobarometric ratio. These are published as metamorphic history records, which are available in GeoView or the bookshop. Those are analogous to geochron records, but we also include in the data layer preliminary data that hasn't been fully QA/QC'd or written up as records. Okay, so that's all available through GeoView. There's a QR code that takes you to the Metamorphic webpage where you can link to GeoView from there. All right, I'm going to just go through very quickly the results from the West Yilgarn, mainly. And this has been touched on a bit by Raf very quickly, but in terms of age, so these are the metamorphic ages we tend to get. This is really only depicting the data from samples that we've done pressure temperature work on, so that we're getting a lot more metamorphic ages out of the terrain that are not represented here. These are just PT samples. And really what we're seeing, what we've known for a long time, is that metamorphism in the Yilgarn and the old southwest terrain really does seem to show a protracted spread of ages from about 2620 to 2665. And it's been hard to know if that represents different pulses of metamorphism or if that really is a protracted event. That's the data that we have. In terms of pressure, Raf also mentioned this, we tend to get a range of mid to upper crustal pressures, but we do see a spike, and that's obviously largely biased by the data set that we have, but we do see a peak of metamorphic pressures from about 4 to 7 kilobar, which is recording paleo depths of about 15 to 25 kilometers. So we are really looking at a mid to upper crustal slice through the crust. In terms of temperature, we generally see ranges at this stage of about 500 to 850 degrees Celsius with a strong grouping just above the solidus, so sitting at about 760 to 900 degrees. Obviously, again, that's largely a function of where we have been able to get samples amenable for this type of work. So we're slightly biased by the high temperature realm of this data set. However, that's where the thermal gradients really come into play. This is a way to normalize the variability we're seeing in the PT data into something that we can use. Okay, so this shows the thermal gradients for this data set, and anything above 150 degrees per kilobar is sitting in the ultra-high pressure temperature window. These are high thermal gradients, okay? We know something funny is going on. So, to really kind of get a sense of what can drive these high thermal gradient metamorphism, I want to return to this geochemistry data set that Hugh's just presented. Aside from all the things that he's mentioned about it being useful for, it's useful for the metamorphic side of the story too, because it can tell you a lot about the thermal history. Now, this diagram here shows the calculated heat production for the granite data set. And this is based on the concentrations of the heat-producing elements being potassium, uranium, and thorium. Now, it's a very detailed image. I don't expect you to appreciate all the details, but what I want to first draw your attention to is the blue line on the top is kind of what's considered to be the standard global granite average for heat production, which is about 2.5 microwatts per cubic meter. And then the red line below it are previous estimates of the Yilgarn felsic average, which are a little bit lower, sitting at about 1.9. A lot of the data that we have is elevated with respect to these kind of normal averages. And in terms of a context that's a little bit easier to distill, we've got the high calcium granites, so the typically older TTG-like compositions in the black box, the low calcium granites in the red box, weird granites with a lithospheric source sitting in the blue, and then we've also compiled some lithologies that make up the greenstones shown in the green. Now the present day, those were present day values, those are going to be minimum values because of the decay of the heat producing elements. So this diagram shows the same data set, same scale of heat production, but calculated for 2640. And not surprisingly, what you can see is that now a lot of these granites are really showing evidence for high heat production. Okay, so surely this is important. It's not just me, right? All right, just to look at this one more time, this shows the data set for samples that have been dated. So we've gone from now 5,500 geochem samples down to just over 500. And this is the heat production calculated for the granite crystallization age. And I know it's hard to see the numbers, but basically the blue circles and squares represent these high calcium granites. And you can see they are fairly elevated with respect to crustal averages. And then you get that huge spike of the low calcium granites at about 2.7 onwards. These are ridiculously high heat production values. Okay, another way to see this is these are contour maps for heat production based on this granite geochemistry database. And anything darker than the darkest green is higher than average. So this is the present day. Now this is the surface level that we're looking at. I'm not suggesting the entire crust was behaving like this, but this is what we see at the surface, that we are looking at vast tracts that are significantly elevated in their heat production. The blue crosses are the surface heat flow measurements, which end up becoming quite helpful later on. Okay, and again, this shows the surface heat production then back calculated at 2640. And again, anything brighter than the darkest green is higher than average modern values. And I mean, anything in the realm of 5+ is extremely high. Okay, well, anyways, so what this stuff begins to tell us is that we're looking at very high heat production. But really what we want to know is what was the depth distribution of these heat-producing elements with time? And what were the thermal effects of that on what we see? Okay, so to address that, I ran some fairly simple 1D thermal models. And it's a simple crustal column composed of crustal layers, which I'll elaborate on the next slide. In this case, for the present day, we've got a lithosphere thickness of 225 is what I used. And the top temperature is fixed at 10 degrees. The bottom is fixed at the LAB temperature of 1300. Now it turns out that temperature at the bottom, you can fiddle with that quite a bit, and it doesn't actually change what's happening in the crust. And then steady state conductive heat transfer equations were solved using the program SheMat. Okay, so before I show you the results, I just want to talk a little bit more about this present day model setup. So this is the basic geometry that we use, which was largely based on the seismic lines and kind of our understanding of what's sitting in the crust, what's coming from where, based on granite petrogenetic models. And I do want to emphasize that this crustal geometry is based on the U and me lines, so the ones further to the north than from where a lot of our data sets come from. It will be really interesting to see how this compares to what we're getting out of the seismic lines or the Midwest lines. But this is the U and me architecture. We've got a thin layer at the present day of low calcium granites with a bit of greenstone sitting on the top. We've got the transitional TTGs, which is kind of the Austin down supersuite, which I represent as a mix. And then we've got this vast tract of unexposed material in the mid-crust, which we've called the Yilgarn seismic province. Okay, this is not exposed anywhere on the surface that we're aware of. So this is quite a big unknown. And then a lower crust and of course, the lithospheric mantle. In terms of the heat production, these values show the median heat production for the appropriate rock types. Okay, so we're looking at, in the present day, a fairly elevated upper crust, slightly elevated lower upper crust, a completely unknown mid-crust, and then the lower crust and lithospheric mantle. All right, so getting a handle on what this Yilgarn seismic province is really important if we want to make any progress in this space. So what is it? Well, it turns out that using the measured surface heat flow can tell us a lot about the potential heat production of that unit. And this diagram on the right just shows a box and whisker plot of the surface heat flow from the West Yilgarn, and it really shows a nice, both the median and the average calculate at about 45 milliwatts per meter squared. Okay. And that ends up being helpful because if I take these models and calculate the heat flow throughout the crustal column, I'm basically looking for a match at the surface that matches the observations we see. And when I do that, it shows that the Yilgarn seismic province has a very low, or a pretty low heat production value of 0.8. Okay, so why is that useful? Because that does match the median value for a sodic diorite. Am I suggesting that that's a sodic diorite? Not necessarily, but it gives us a really useful range of compositions when we start thinking about past heat production through the crust, through the part of a crust we know nothing about. Okay, this looks very complicated. It actually is a very, very simplified figure. And these are the 4 models that I've run. So we've got model 1 is our best guess of the Proterozoic. Okay, we've got a layer of greenstones. We've got the older high calcium TTGs. We've got the Yilgarn, we've got a mafic lower crust, and then the lithospheric mantle. That's model 1. Now I should emphasize that these time slices are not really that important in the terms of the model. These are steady state models, so whether I call model 1 2.9 to 2760, 2.9 to pick your number, it doesn't actually matter. Model 2, there's a lot happening in this time period. Yeah, this is from 2760 to 2650. Again, I could change these numbers. What we're trying to represent here are the reconfiguration of crustal layers and the impacts on heat production. If I complicate these models, I introduce more uncertainty. So I am intentionally trying to keep these models simple to kind of test this hypothesis. Okay. So model 2 represents kind of this next major reconfiguration of heat production where we've got the final deposition of greenstones, we've got the intrusion of high calcium granites, this Austin Downs type lithology, which is in reality a mix. We've got then underlain by the older TTGs and so on. A bit of crustal thickening there associated with Yilgarn orogeny. But that's what that's showing. I should also point out that these red arrows are where the heat producing elements are coming from. Okay, so we know the source for this layer 6, this high calcium Austin Downs high calcium Austin Downs granite. We know that it comes from the older TTGs, this unit 2. We know it comes from the lower crust. So it fiddled a bit with balancing the heat production so that this is a consistent crustal column. Okay, then model 3 is what we think is about 2650 onward, where we've got a granite greenstone upper crust, a layer of low calcium granites, which is this unit 5, quite high heat production, relatively thin, and then the Austin Downs below it, and so on. And then the present day, which we used to kind of help us characterize the Yilgarn. Okay, so in terms of the results, this shows the calculated geotherms for each of these 4 models, with the average continental geotherm in the dashed line. The black is the present day, shows that it's quite cool, which is what we would expect. And then the blue line is model 1, so the oldest stage. Green line is model 2, where we start redistributing things, but it doesn't really have that much effect on the thermal structure. And then model 3, even though we've added this layer of high heat production into the upper crust, we actually start to cool, which isn't surprising given the decay of these elements. So now in terms of marrying this up with the metamorphic data, this is the value of having metamorphic data. Well, not going to lie, I was a bit disappointed with this result. What does pop out nicely, I think, is that the geotherms for models 1 and 2, so the green and the blue, do match up with kind of the deeper, the metamorphic data from deeper in the crust. But we do see a lot of data points that are recording higher thermal gradients. So what's the deal with that? Okay, well, if I add in now the thermal effects of emplacing granites, it does start to capture some of this data. This is a really brute force way that I did this. It's not the most elegant, and simply what's happening is I'm holding the temperature of that unit 5, those low calcium granites, holding it constant at 700 degrees. But it demonstrates that if you've got this granite coming in, and we know we've got protracted magmatism for a long time, it might actually start to capture some of the information we're getting from the metamorphic data. And this isn't surprising. I mean, these thermal gradients, especially when you're sitting up at 8 kilometers, those uppermost ones, you need granites for that. You can't do that without it, I don't think. Okay, so this suggests that, yes, we do see the thermal effect of granites in the mid to upper crust, which is consistent with this idea that large parts of the Yilgarn record regional contact metamorphism at about 2640. So that does seem to be consistent with what we're seeing. All right. But what about crustal melting? How are we getting these granites? We know the granites are being reflected in the metamorphic record, but what's causing the granites? We need to produce them somehow. Okay, so this diagram, again, shows the predicted geotherms in the solid lines, but I've now superimposed the various solidi of different compositions. So we've got the tonalite wet solidus in the blue, biotite dehydration melting in the brown, and then the amphibolite solidus at the highest temperature. And obviously, the exact locations of these melting curves are going to change, depending on slight differences in water content and composition. But what we're looking for is where the geotherms cross over these solidus in order to think about depths or conditions of melting. Okay, and the next diagram will show the crustal columns from Model 2. Be on the edge of your seat. All right, well, anyways, so, okay. So, again, this is from Model 2, so kind of the peak of when we have a lot happening. And what we're looking for is when the green curve crosses one of the solidus lines. And lo and behold, I was not very happy to see that it basically crosses the solidus at the very base of the crustal layer that I've devised. So, okay. So what that's telling us at a first pass is that, okay, the crust is thermally primed for melting due to radiogenic heat. Any additional thermal perturbations, whether that be mafic input or magmatism, is obviously going to help promote more melting and help the story. But what about model uncertainties? Okay. This isn't a very satisfying route to go down, but I'm going to take you there anyway. So there's obviously uncertainties on all of this. The metamorphic data that I've shown you have uncertainties. The calculated geotherms have uncertainties. The heat production values I put in have uncertainties. But a significant source of uncertainty in these models is the thermal dependence, or the temperature dependence on thermal conductivity, which is used to solve these heat transfer equations. And this is a significant unknown. There's no one equation that fits all. These are dependent on lithology, they're dependent on mineralogy, grain size, a whole slew of variables, so that we can't take one equation from the literature and pop it into this terrain and expect to get the right answer. That said, I did try. I've taken one equation for the the temperature dependence on thermal conductivity, and these are now the very heavy lines, and it shows you that there is a temperature shift, and we know this. I mean, previous estimates on other cratons that have done similar studies show the uncertainties, not just on thermal conductivity, but also just the heat production, are on the order of 50 to 100 degrees Celsius. So when we consider the temperature dependence, which we know is real, we can expect temperatures to increase. How much? We don't know. So what that means is that Now the depth of melting becomes a lot shallower and potentially more realistic with what we might see. Am I saying this is the answer? Not necessarily, but it is certainly suggesting that the radiogenic heating is priming the crust. Okay. So I guess that's really my conclusion there. So this work, we do know, or we have demonstrated that the Yilgarn crust is more radiogenic than previously thought. So that's an important outcome right there. I believe that radiogenic heat really did thermally prime the crust for melting. And an implication of that is that the crust would have remained hot for a long time. And then we also see that the metamorphic record that's preserved was driven by radiogenic heat, but also in some cases did require the input of magmatism, such as Tony suggested as well. All right, thank you for that whirlwind.